environments, that's how molecules fluoresce. But if you can generate very high photon density at the focal plane, and by that I mean sufficient photon density to strike the fluorophore in quick succession by 2 or more photons, in like a femtosecond faster, then the fluorophore can be tricked into thinking it's been hit by, even if these are long wavelength photons, can be tricked into thinking it's been hit by a single photon in the excitatory wavelength. And so what this translates to is you can use red light or near infrared light around 900 nanometers to excite GFP. And the technical advantage is that the biological tissues are minimally, they show an absorption minimum around 800 nanometers to 1,000 nanometers. So light of that wavelength is particularly penetrant. And the only place that, if you tune your optics correctly, the only place that the multi-photon effect occurs is in the focal plane. And so there's the signal-to-noise ratio is very, very high as a result. So you can use long wavelength light to strike the fluorophore by GFP, it fluoresces, and the only place that fluorescence occurs is in the focal plane. The excitatory light is long wavelength, so it can get deeper into the brain. The green light that comes out still has to get out of the brain, but you can image on the order of, I mean, practically we can go about 600 microns in the brain, which can take us all the way to the floor of HPC.
Do you have to cut a hole in the skull to do that?
In these experiments, we make a small cranial window. So what we do is we make a very tiny hole in the skull. It's really small, it's less than a millimeter square. We cut by hand a tiny little glass cover slip and then cement that in place. And so it really is a window into the brain. But the bird can sing, you know, and other birds don't seem to notice the tubes sing to it. So.
A couple of times you referred to a clock in HPC, and I guess that would contrast to the chain hypothesis that was briefly alluded to. So I was wondering whether you want to specify a little bit what you mean by a clock in HPC.
Well, there's no doubt. I mean, if you cool HPC, it's not long and microfeedback, and you cool it, you know, over a range of 5 degrees Celsius, the song tempo slows and slows and slows. And at least at first glance, it looks like there's pretty uniform stretching across time scales, although there's some debate about that, and that's actually really important for the question. So that's one piece of evidence that there's some kind of timing information in HPC. Another is this unit activity, which fires, the HPC RNA neurons fire once per song phrase, and if you report from a dozen or so of these, you can find them fire at different times, and so if you extrapolate the population of 40,000 HPC RNA neurons, that is an kind of continuous representation of time across this population of neurons. The simplest model to achieve this is some fire chain is both of HPC, and I think that model is wrong. I think it's wrong, both based on the synaptic evidence we're collecting, and if you push the cooling further beyond about 6 degrees Celsius, Gabriel Newman's lab has done this experiment, the song breaks, and it breaks and you get doubling of syllables in a way that can only be accounted for by a model that has a recurrent loop that extends outside of the cooling zone and somehow acts as inhibitory circuitry, kinetic inhibitory effect. So current evidence maybe is it look like little local chains that produce part of the temporal information, but they're looped through recurrent architecture that generate continuity. And there's some evidence that that's the way it's built.
Thanks.